Okay, now we're at the plane of light, the full screen illuminated as brightly as it can, given the monitor I have. I'm trying to stay consistent with the brightnesses in all of them. And when the light sensor is right up against the screen, this is the value that we're seeing. I'll just run it again. It's clearly a little bit brighter than the point, the case with the point. Not a lot, which tells me that the point was a pretty wide point, almost covering the same amount of area as the screen at this point. The difference is the screen, full screen illumination is going to drop off less rapidly than the point. So at the beginning here, it's 103 lux. Now I'm going to back it up a half centimeter. Okay, now I'm a half centimeter away from the full screen. Look at that. It's almost the same as it was when it was right up against the screen. I'm emphasizing that for a reason. I have 102.6. I'm going to go to a centimeter now. Okay, a centimeter away from the screen, we are at 102.4. Okay, now we're at 1.5 centimeters away. And I'm seeing 102.5. So it hasn't really changed much. Hasn't really changed much. Okay, I'm now 2 centimeters away. I think that's right. Yeah, 2 centimeters away. And I am at 102.3. Again, it's staying pretty constant, isn't it? Okay, I'm at 2.5 centimeters away. $102.6. We're now 3 centimeters away. I know the thought on your mind is, when is that brightness going to start to decrease? Well, it is eventually. It's on my mind too. How long is it going to take till we start seeing a noticeable decrease in the intensity? Whoops. Accidentally collected again. All right, it is 101.5. Small decrease here. Small decrease. At 3 centimeters, 101.5 lux. Okay, now we're at 3.5 centimeters from the fully lit screen. And 101.8. 3.5 centimeters. 101.8 lux. Okay, we're now 4 centimeters away. Press collect. And 101.9. And move to 4.5 centimeters now. 4.5 centimeters away. Let's see what we got. 101.2. Okay, we're now 5 centimeters away from the fully lit screen. 101. Next stop, 5.5. Okay, now 5.5 centimeters away from the fully lit screen. 101. Whoops, I forgot to pause it. Okay, we're now 6 centimeters away from the fully lit screen. $100.6. 6.5 centimeters away from the fully lit screen. $100.3. Next stop, 7 centimeters. 7 centimeters from the fully lit screen. Does this thing ever go down much? Yeah, 100. Not much. It's an infinite plane, or close, not quite. But to somebody really close to it, it looks pretty infinite. I'm going to keep going. 7.5 centimeters away from the fully lit plane. The light sensor is recording an illumination on the average of 100.1. lumens, or lux, 100.1 lux. All right. 8 centimeters is... Okay, we're 8 centimeters away. Looks like it might have dropped ever so slightly. Maybe. What I'm seeing is 99.2. Wow, broke that 100 mark at 8 centimeters. 99.2. 8.5 is next. 8.5 centimeters from the plane of charge. $99.1. We're at 9 centimeters from the plane of charge. I see 98.8 lumens. $9.5 centimeters from the plane of charge. $98.6 lumens. This is it, folks. 10 centimeters from the plane of charge. Compared to the earlier one, it went down a tiny bit, but not much. 98.4 lumens. Okay, you might have had something like this happen to you before. Happened to me as I was doing the last set of measurements. I realized because I don't have a great ruler here. I'm using this piece of cardboard that has measurements on it. And there's like this 0.5 centimeter offset that I thought I incorporated when I was making the measurements, particularly for the point and the line, that I don't think I really did a great job at. And you've probably been at that point in lab where in some labs sometime where you realize you made a mistake and you made all these measurements that weren't right, and you hated to have to redo everything, but you did it, and in the end you were probably happy because you had better data? Well, that's what I'm going to do. So it happens to me too. I'm going to redo the point and the line, and it'll be faster this time because I've done it before, but I want to redo them and get better data, at least for every centimeter, so that I can try to correct this and so you can get a better graph later. And I'll talk to you about the graph in just a couple minutes. Rather than dragging you through all the measurements like we did a little while ago, I redid them for the line, I'll redo them for the point and read them to you and say that it closer to the screen for the line, I think there was some error in how I was making the measurements. So the redone measurements are as follows. 10 centimeters, distance the furthest away for the line, 4.7 lux. At 9.5 centimeters, 4.9 lux. At 9 centimeters, 5.1 lux. At 8.5 centimeters, 5.2 lux. At 8 centimeters, 5.6 lux. At 7.5 centimeters, 5.7 lux. At 7 centimeters, 6.1 lux. 6.5 centimeters, 6.6 lux. 6 centimeters, 6.9 lux. 5.5 centimeters, 7.4 lux. 5 centimeters, 8 lux. 4.5 centimeters, 8.7 lux. 4 centimeters, 9.5 lux. 3.5 centimeters, 10.5 lux. 3 centimeters, 11.8 lux. 2.5 centimeters, 14.4 lux. 2 centimeters, 16.2 lux. 1.5 centimeters, 19.6 lux. 1 centimeter, 28.2 lux. Half a centimeter, 39.4 lux. And at 0 centimeters, right up against the screen, 74.4 lux for the line of charge. The next one I'll do is the point of charge, and I'll read those to you after. All right, I just repeated the measurements for the point, and I'll take them from right up against the screen, backing out to 10 centimeters. Right up against the screen, it was 101 lux. 0.5 centimeters from the screen, 52.1 lux. 1 centimeter from the screen, 30 lux. 1.5 centimeters from the screen, 19.4 lux. 2 centimeters from the screen, 13.6 lux. 2.5 centimeters from the screen, 9.6 lux. 3 centimeters from the screen, 7.4 lux. 3.5 centimeters from the screen, 6.2 lux. 4 centimeters from the screen, 5.1 lux. 4.5 centimeters from the screen, get this, 4.5 lux. 5 centimeters from the screen, 4 lux. 5.5 centimeters from the screen, 3.7 lux. 6 centimeters from the screen, 3.2 lux. 6.5 centimeters from the screen, 2.9 lux. 7 centimeters from the screen, 2.8 lux. 7.5 centimeters from the screen, 2.6 lux. 8 centimeters from the screen, 2.5 lux. 8.5 centimeters from the screen, 2.4 lux. 9 centimeters from the screen, 2.2 lux. 9.5 centimeters from the screen, 2.1 lux. And 10 centimeters from the screen, 2 lux. This is for the point on the screen. Okay, and I just want to say a word here, and then I'll show you about the data in just a minute. Part of science sometimes is the tediousness of it. It's not all glamour, and sometimes it's just getting down and making the measurements and investing in them and making sure they're as good as possible. And so that's what I attempted to do here. And you may find yourself in that situation in this class or other classes where sometimes it's just getting down to sitting with something for a while. Almost have to be zen about it and go through the motions and invest in it at the same time. All right, just a little word of, I would say, wisdom or reflection during this lab. All right, I want to show you what to do with the data, and I'm just going to take the data from the point in this case. So in this column here, we have the distance from the screen for the point, and the distance is in centimeters. And in this column here is the brightness in lux that we recorded. And one point I want to make is the 0, where I had a 0 centimeters. I'm giving that a value a small, tiny little value other than 0 for a couple of reasons. One is that in doing some of the mathematical operations we're going to do, we don't like taking 1 over 0. We're going to be doing that in just a couple minutes. And the other reason is when I'm actually making measurements of the brightness, am I actually looking at the surface of the brightness where there is 0 distance between the source and the receiver? And that's not the case. Matter of fact, I don't know if that's even possible to do. So many of the particularly the smaller values are going to be slightly erroneous in that because you don't really know where the source of brightness is. And even if you did, you can't make your sensor be 0 distance away from it. You have to be some distance away from the bright source in order to have the 1 over r squared dependence that we suspect will be the case. Furthermore, for these close data points, we don't really truly have a point. It looks more like a plane because the dot is so big. All right, so it's kind of dying off much more slowly here than we might expect it to otherwise. We'd expect it to die off faster if it were truly a point. So those are just a few reasons why this is not a 0 here. But I do want to start by plotting it. So I'm going to insert a scatter plot. There we go. And I like to label the axes. The default doesn't have the axes labeled, so I go under the Format for Chart Tools. Design for Chart Tools, and I go Add Chart Element. And I pick Axis Titles, and I'll make the horizontal axis title the distance from point source, centimeters. And the vertical title I will make lux, which is the same as the actual title, but I want to change the actual title to be a little bit more specific. I'll make that be lux versus distance from source. All right, so that's a more complete graph. The other thing we can do is we can actually put a trend line in here so that we see how closely does it match to a power function, which is what we think it might be. Power function, we thought it should look as 1 over r squared. Well, let's see what Excel says. When I add a chart element, I can tell it to do a trend line. And I can say more trend line options because none of these have the power option, which is what I'm looking for. And let me see, didn't come up. Let me try it again. More trend line options. There we go. Power. That's what I want to see. And I want to display the equation on chart. It's telling me the equation that it thinks it looks like is this. Make it bigger if I can. If you can see it. That's far from 1 over r squared, but as I mentioned earlier, the points that are closest to 0 are the ones that are the least likely to follow the 1 over r squared rule because this isn't really a point source. So I'm going to take points further away, starting at, say, 2.5 centimeters. I'll graph those. And I'll insert a trend line in this one, just to show you it should look a little bit closer to 1 over r squared, some function of over r squared. It won't be perfect either, but it'll look closer. So go Design, Add Chart Element, Trend Line. I go to Power. And it's telling me, display equation on chart. Make that bigger. It's certainly not 1 over r squared here either, but it's closer than it was in that previous one. So those first data points are more problematic from looking at it as a 1 over r squared function, the inverse square law, but it's getting closer as we take points further away. All right, so another way we can look at this too is to plot. I'm going to copy this column to here, but I also want to try plotting this as 1 over r squared, or 1 over the distance squared. So I'm going to take this and say 1 divided by this value squared, and I'm going to drag that down, and the numbers are going to get much smaller, very small, very quickly there. All right, so I took 1 over r squared, and let's plot that. I'll get this superscript here. That's subscript, but superscript. There we go. Insert graph. And that doesn't look very good. But this first data point here is dominating everything. Look how big. That's 10,000. The next one is 4. I'm going to get rid of that first data point because even that close it's going to be very difficult to plot that relative to the other ones. Now the idea here is that this should look something like a line. And as I mentioned, those close data points are off from the 1 over r squared. But if you look at these here, you can see that these here are starting to show what might be construed as a line, which would be what a 1 over r squared dependence would look like if you were plotting it as lux versus 1 over the distance, which is what this is down here. Just to emphasize that, I'm going to label that axis to show that it's 1 over the distance squared. So I'm going to make that a superscript. Probably have to enter it first and then put it in here. There we go. Okay, so this is lux versus 1 over distance squared. You can see that it's semi-linear. I'd say the first part here over on the left, these here, where the cursor is approximately, that's closer to looking like it could be linear, though it's still not perfect. But this gives you an idea of how you can start looking at the function differently. For the line, you're going to be looking at it as 1 over r. And for where I just use the continuous plane of brightness, you're just going to plot that. And that should be relatively constant. You'll see that it is. Okay, I hope this lab gets you to think about how things vary, how a plane is going to look pretty consistent as you get further away from it, up to a point, when you get far enough away from it, it's going to start looking like a point eventually, and it's going to start going as 1 over r squared. And the point should go as close to 1 over r squared, and the line should look something like 1 over r. That's really what I want you to get out of this lab. Think about the uncertainties. I've been telling you a little bit about them. There's a measurement error too, probably on the order of 1 millimeter or 2. There's a variation in the brightness, which is some level of uncertainty. But when you really get close to a bright source, particularly a point source, getting that distance and knowing that what that distance really means, there's an uncertainty that lies there too, as I mentioned earlier in this portion of the video. Okay, good luck with the write-up.